Welcome to the short-term course and faculty development program conducted by the Department of Electrical Engineering, National Institute of Technology, Rourkela. Now, the speaker of the present session is Professor Pravat Kumar Rai, sir, Head of the Department, Electrical Engineering, NIT Rourkela. Now, let me introduce Professor Pravat Kumar Rai to you all. Professor Pravat Kumar Rai received the BE degree in Electrical Engineering from Indira Gandhi Institute of Technology, Sarang, Odisha in 2000. The ME degree in Electrical Engineering from Indian Institute of Engineering, Science and Technology, Shibpur, Howrah in 2003, and the PhD degree in Electrical Engineering from National Institute of Technology, Rourkela in 2011. He had worked as a postdoctoral fellow from January 2016 to June 2017 at Nanyang Technical University, NTU, Singapore. He is currently serving as professor and head of the Department of Electrical Engineering, National Institute of Technology, Rourkela. He has around 22 years of experience in teaching and research. He has supervised 15 PhD students. He has published his research outcomes in around 100 research papers in reputed journals, including IEEE Transactions, IET, and Elsevier, etc. He has edited 3 books, contributed 18 book chapters, and around 122 conference papers. He is involved in research project work sponsored by funding agencies such as DST, DST UKRI, Imprint2, SERB, Indo-Asian, and Indo-Thailand, etc. He has visited 7 foreign universities, which includes Queen's Mary University of London, UK, University of Southampton, Malaysia, University of Mataram, Indonesia, Walailak University, Thailand, University of Mortava, Colombo, Sri Lanka, etc. As a part of bilateral collaborative research, he is working as associate editor, IEEE CSEE Journal of Power and Energy Systems, and as guest editor of a special issue entitled Advances in Control of Photovoltaic and Microgrid Systems, Energies Journal, MDPI publisher. His research interests include estimation and filtering in power system, power quality, power management in hybrid AC/DC microgrids, smart grid, solar irradiance forecasting, and renewable integration. His name has been listed in world's top 2% of most cited scientists for the year 2024 as per Stanford University and elsewhere. With this one, I request Sir to address the participants. Sir, please.
Thank you, Pranati. Now my screen is visible.
Yes, sir, it's
Yes, sir,
visible, sir.
visible.
Okay. So today we'll discuss regarding power quality improvement and power flow analysis of a grid connected photovoltaic system. So here we'll cover basically in the introduction section, I will discuss regarding what is a simple microgrid. So how to improve the performance of a microgrid, different ways or different techniques or different methods. Then key concerns regarding operation of UPQC. So before that, what is power quality and why power quality improvement is required? Then what is UPQC? Whether we'll go for both the voltage quality improvement or current quality improvement or individually. So if you'll go for both the voltage and current quality improvement, then you have to go for this UPQC. That we'll discuss, that is unified power quality conditioner. Then contributions of the means what are the main contribution regarding this work? Then the schematic or system under consideration. Then so far as methodology is concerned, 1 minute. So far as methodology is concerned, so generation of reference DC link voltage of UPQC and adaptive fundamental frequency estimation. Why we have to go for adaptive fundamental frequency estimation? What is its necessity? regarding to this research or this work. Then what is COM filter and second order harmonic oscillator CFSOHO, and why you have to go for this normalized CFSOHO, that is NCFSOHO best unit template generation. And after the generation of this unit template, the next step is reference voltage signal generation, voltage generation for the series compensator, because UPQC having two converters or two compensator. One is series compensator, another is shunt or parallel compensator. So we have to generate switching signal for both the converters. That's why reference voltage generation required for series compensator and reference current generation required for parallel compensator. Then regarding whatever we'll discuss here, its simulation results discussion and its implementation or the verification using experimentally developed prototype, some conclusion references. Now coming to this brief overview on a microgrid. This is a simple microgrid where this is the grid. Photovoltaic is connected to the grid but through UPQC. So UPQC is responsible for power quality improvement. So PV is connected to grid through UPQC, and for PV, in order to address its intermittency issue, we have to go for forecasting of solar irradiance. And what are the different methods? In brief, we will discuss. Then regarding energy management for economic dispatch, we have to implement in a simple microgrid. And another part is regarding demand response management, how demand response management improve the performance of a microgrid. Then another thing is regarding the storage devices. So here we have implemented a combined storage device, that is battery and supercapacitor. And this combined storage device integrated to the system, microgrid system, through SST, solid state transformer. So these are the different things in a simple microgrid having PV only. So what are these areas or what are the challenges associated with it, and how can we improve its performance? So some of the areas are: first is intelligent generation control based on forecasting and load management scheme. What is that? What you have to do, that also discuss in brief. Then obviously the talk of today, that is UPQC with advanced controller to improve the power quality of microgrid. Why power quality issue is more acute in this microgrid, and what are the necessary techniques to improve power quality, and what is UPQC in detail, that we'll discuss. Then what is basically demand response management? How can you implement this one, and what are the benefits of it? Next is the advanced hybrid energy storage system with solid state transformer interface. We've already discussed this is a hybrid energy storage system. It is interfaced with the system through SST, solid state transformer. Then optimal energy generation scheduling in microgrid with uncertainty. Why you have to take into account uncertainty? What is its necessity in microgrid? That also we'll discuss in brief. So if you tackle all these issues or more than one issues of this microgrid, then you can enhance the performance or improve the performance of microgrid. Now coming to first point, intelligent generation control based on forecasting and load management. So while talking about microgrid, here we have already discussed that PV is the main candidate, that is generating source. So, but the main issue lies with the PV is the intermittency or variability issue. So how can you address that issue? So this thing more or less I have already discussed on the inaugural session. That is, while addressing the issue of this intermittency nature of photovoltaic, so first is we have to go for forecasting. So nowadays, or previously the method used was the model based, but nowadays image based forecasting also came, but not prominent in India. In other European country, Singapore, that is Southeast Asian country, these are prominent. So that means what is the difference between model-based solar irradiance forecasting and image-based solar irradiance forecasting? So model-based, all of us know, just like any type of forecasting or estimation, you have to take the data from different meteorological sites. We have to collect data, maybe 5 year, 10 year, 20 years data, then use any artificial intelligence algorithm or system attention algorithm. Using those algorithms, we can find out, or you can forecast, or you can estimate what will be our solar irradiance on a particular day, because we have given input, or we have trained our system giving the previous data. That is one method, that is a very conventional method. So earlier days it was also used. But now, to get more accuracy, that solar irradiance forecasting is done using sky image. That is sky. For that, sky imagers are to be installed on the rooftop of a building, different buildings. So sky imagers will capture data, image of sky, means sky image, it will capture within maybe 30-second duration, one image it will capture. Then those images will go to server. Then from the server, taking those images, now image and previous 1 minute ago image, between these two images, we have to compare using image analysis technique, using image processing technique. Then we'll find out if 1 minute ago the image position is like this, and after 1 minute the cloud position is like this, after 1 minute the cloud position is like this, then what is the movement of the cloud, that will determine. And for example, we want to forecast after half an hour or after 1 hour, what should be the solar irradiance. Then using optical flow algorithm, we can find out if this is the movement of the cloud, or the cloud is moving at this speed, then after half an hour or after 1 hour, the which portion of the cloud will cover the sun. For example, let we determine that thick cloud portion will cover the sun. Then some analysis is there, we can find out that, and for a particular day, for a particular place, we have to take into account different data also. So from that we can find out that our solar irradiance will be this much. So this is very accurate, not completely implemented in India. Other European country and Southeast Asian country, all these are now implementing. So this is another method. So that means using either model based or image based method, we can forecast our irradiance. That means what will happen then? If you know our irradiance will be this much on a particular day and a particular time, then we can find out that how much generation we'll get from PV, and accordingly we'll adjust some other generation. If PV is low, then we can go for some other generation, switch on other generation. If PV is high, then we can switch off other generation. So like this, we can meet our load demand. So online intelligent generation control will be developed that will ramp up auxiliary sources when there is shortage, and will store, if there is more energy, it will store the excess energy in hybrid energy storage system if energy generated is surplus. So this is regarding intelligent generation control based on forecasting and load management. Next one is the development of unified power quality conditioner with advanced controller to improve the power quality of microgrid. So now, why you are more concerned about this power quality in a microgrid? Because we may be less concerned in the power quality in the general grid, but more concerned about power quality in a microgrid. Why? Because when we are talking about microgrid, here so many distributed energy sources are connected to grid, and each distributed energy source will require a power electronic converter to be connected to the grid. So for that, so when so many generating sources are there and so many power electronic converters are connected, then power quality deteriorates. How deteriorates, that also discuss in subsequent slides. So when power quality deteriorates, then our aim and objective is to improve the power quality. Just like I have discussed, if we are more concerned about current quality improvement, then we have to go for active power filter, shunt active power filter. If you are more concerned only about voltage quality, then we have to go for series active power filter. But if we require both our voltage and current quality is to be good, or we want improvement in both the cases, then we have to go for UPQC, where both the converters, both series and shunt active filters are there. Next is development of an adaptive demand response management for microgrid. So basically, from the name it indicates demand response management. So we have to manage in the our demand. So which way we have to manage? That is our lookout. So basically, demand response management main aim is to bring down the cost of electricity generation by reducing the peak load and shifting the peak hour demand to off peak hour. For example, if you want to use your washing machine in the daytime, say at the daytime the tariff is high, you have to pay more, then you may lose your comfort. You may use in the night time when maybe the tariff is less. So that means you are shifting your demand. So when you shift your demand, peak, if everyone will shift like this, or the more number of people will shift like this, then obviously the peak demand, peak load means reducing the peak load. Obviously peak load is also reduced. And here also to propose a distributed energy scheduling algorithm to find out which one is our means most optimal operating time and energy consumption. That you have to find out using algorithm for the appliances by minimizing. In that way, we can minimize the overall cost of operation. Now coming to fourth one, development of advanced hybrid energy storage system with solid state transformer interface. Now, first question, why we have to go for this hybrid energy storage system if only solo storage system is enough or there, then why we have to go for hybrid energy storage system? See, when if let us take we have used only solo storage device, say battery, then when there is sudden load change, then battery has to act on that instant also. That means that is the transient case. So battery has to act both in the transient and steady state case. If always battery will act both cases, transient and steady state case, then health of the battery may deteriorate. So for that, in order to handle this sudden transient cases or jerk when came, sudden transient when came, that if we handle by supercapacitor, then battery may be relieved by that time. So in that way, we can maintain the health of battery. That's why better to go for hybrid energy storage system. Next is why solid state transformer interface is required. Because solid state transformer is nothing but power electronic based transformer. When their power electronic is there, then more flexibility in control is there. That means we can generate our switching signal as per our algorithm or as per our control, then more flexibility in the charge and discharge. So that's why to implement isolation, bidirectional power flow and more flexibility in the charge and discharge control, we have to go for solid state transformer. So by that way, we can improve the efficiency or performance of a microgrid also. Another is optimal energy generation scheduling in microgrid with uncertainty. So first question, why you have to go for uncertainty modeling? See, when first of all, we have already discussed that when so many renewable connected and different renewables are having intermittency in nature in so far as their generation is concerned, and nowadays more electric vehicles are coming to our power system also. That means electric vehicles are taking charge and also giving charge. That means we don't know when a EV can take charge and when a EV can discharge charge, because it depends on the owner when he can use for charging or he can use for discharging. That's why. That means our source become uncertain. If EV will provide, when it will provide, that also we don't know. When it will take, that also we don't know. So our generation is uncertain, our load is uncertain. So if you not follow the uncertainty modeling, then whole analysis will get the wrong analysis or wrong result. That's why for randomness of demand and renewable generation, uncertainty modeling is to be developed. Then a robust optimization technique to develop to obtain optimal energy generation scheduling policy in microgrid. So these are more or less just brief overview or the problem statements associated with microgrid. So if we handle all or more than one issue, then our performance or efficiency of microgrid will be improved. Now coming to one problem, that is power quality improvement using UPQC. So before that, what is a power quality? From the name it indicates the quality of power should be good. Power quality means quality will be good, quality of power will be good. So from the name or the definition should be stable, no fluctuation, no interruption, uninterrupted, no distortion, means no harmonics present, and disturbance free also. So if our power will get power with all these 3-4 natures, then we can say that our power quality is good. So nowadays it is a critical challenge because of widespread use of nonlinear power electronic load. Just I have already discussed power electronic interface is there. So many loads nowadays are power electronic load. Then what will happen? Why our power quality deteriorates? Because when power electronic load is connected or the nonlinear load is connected, it draws nonlinear current from the source. And when this nonlinear current passes through the impedance of the path, then what will happen? Non-sinusoidal voltage will develop at the load end or the point of common coupling, which leads to poor power quality. So that's why. And what are the effects of poor power quality? If you will not go for improvement, what will happen? Effect of poor power quality will have serious implication on utility and consumer, because this power connected to sensitive loads such as hospital, bank security system, air traffic control. So if we will not maintain the power, if we will not maintain the voltage, then all these sophisticated equipment, whatever connected for these hospitals, say bank security or air traffic, then all get disturbed, their performance may hampered. So that's why there is a requirement for the improvement of power quality, which is the need of the hour. Now coming to UPQC, this UPQC has already discussed that it has two converters. One is series active power filter, another is shunt active power filter. Series active power filter is responsible, or it will go for improving the voltage type of disturbances, whereas current active power filter is responsible for improving the different current related disturbances such as current harmonics, unbalance, etc. And also it regulates DC voltage and compensate reactive power of load. Then another thing is, if there is no source, means during voltage disturbance, for example, sag and swell, why the performance of UPQC deteriorates? Because there is absence of active power support to maintain the DC link. That we'll discuss in detail. Where is the DC link? what support it required, how much for maintaining DC volt and DC voltage, how much current it will draw from the source. In detail analysis also we'll discuss. So if there is no active power support to maintain this DC voltage, then its performance deteriorates. So for that, to give you a support, we have integrated in this work photovoltaic integrated to UPQC, that is a PV UPQC system. Now, what are the different concerns regarding this operation of UPQC? So, when you go for this UPQC operation, it is to be connected, or it is to be connected to the system, means it is to be synchronized. So, for synchronization, what are the requirements? For the synchronization, we want or we should get an accurate estimation of frequency. After accurate estimation of frequency, we can generate unit template or phase information of grid for generation of the reference signal and for synchronized operation of the system with respect to grid. That means for unit template generation is required for reference generation, and for unit template generation, accurate estimation of frequency is required. So first is frequency estimation, unit template generation, then reference signal generation for synchronized operation of the UPQC. 3 steps. So extraction of fundamental component from non-ideal load current is the main challenging thing, because our load current is highly disturbed, full of harmonics, so many harmonic content is there. So from that harmonic component or content, we have to extract the fundamental component properly. Then only our unit template generation will be more accurate and generation of reference signal will be more accurate. So extraction of fundamental component from non-ideal load current is a challenging task. Another is active and reactive power distribution. Here, active and reactive power distribution between different entities such as grid, load, PV and UPQC. So many entities are now grid, load, PV and UPQC. How power management can be done with swift regulation of DC voltage by proper reference signal generation. So these are the different challenges so far as operation of UPQC is concerned. Now, what are the main contributions in this work? As we've already discussed, that accurate estimation of frequency is a challenging task. So here, we implemented an adaptive power frequency estimation, which is based on variable leaky least mean square based notch filter. That is one of the contribution. And another is NCFSO, that is normalized comb filter based second order harmonic oscillator. So that is required for positive sequence estimator to minimize the impact of grid voltage, and that is sag and swell. So that means NCFSO method, how it is implemented, that will discuss. Using this one, we can estimate positive sequence component, and from positive sequence component, we can find out or we can generate our unit template. And after generation of unit template, we have to go for reference signal generation. So another thing is mitigation of voltage related power quality issues with respect to grid voltage utilizing this NCFSO already discussed. So how to improve the voltage quality using this NCFSO method. Then elimination of, next is this above is the voltage related issue. Next is regarding the current related issue. So for elimination or mitigation of current related power quality issue, we have used here the modified notch filter. So what is notch filter and how you have to modify it, and how this modified notch filter is used for this fundamental frequency extraction from the non-fundamental component. That is also one of the contribution. And finally, the swift regulation of DC voltage with respect to available photovoltaic voltage and regarding the power flow management or power flow analysis with varying system dynamics. That means when there is sag, swell, when there is harmonics, how it can handle those issues. This is the schematic or the framework on which the work is based. So this is our system. This is a three-phase source, three-phase load. This is the line. So three-phase source, three-phase load. So now this is our UPQC. So where both series compensator is there and parallel or shunt compensator is there, both are connected across the DC link, across a DC link, VDC. And this DC link voltage is also fed from a photovoltaic system through reverse blocking diode. And when we will go for improving the current quality, we have to feed or we have to inject signal here at the point of current coupling, PCC point. PCC point, you have to inject the current signal while going for this current quality improvement. Then if we'll go for this voltage quality improvement, you have to inject voltage. For injecting voltage, transformer is required. So that's why using this transformer, so you have to inject voltage, three-phase voltage for the voltage quality improvement. If there is voltage sag and swell is there, then you have to inject voltage for improving. For current harmonics, you have to inject current at the PCC point. So in this way, the power quality or this voltage quality, current quality can be improved. But main challenging thing is how much voltage to be injected, how much current to be injected with the variation of the load. That we have to decide. And how we have to decide? Using control algorithm. If there is variation in load, if there is more harmonics present, then how much current we have to inject? That we have to decide using control algorithm. For that, accordingly, you have to provide switching signal to the converters. And this control algorithm, main aim or objective is to provide switching signal for the converters, taking into account different situation, dynamic situation of the power system. So this is the schematic on which the work is based. Now, what are the steps involved for the control of this grid connected PV UPQC system? So we've already discussed the generation of reference DC link voltage of the UPQC is the prime concern because you have to maintain the DC link voltage, otherwise the system operation will be hampered. And also discussed accurate estimation of power system frequency is required so that we can accurately find out or estimate our unit template or generate our unit template. So estimation of system power frequency using VLLMS notch filter, estimation of fundamental positive sequence unit template using NCFSO, then reference signal generation, then obviously two final things, reference signal generation for switching of the series converter, as well as reference signal generation for switching of the parallel converter or shunt converter. So these are the different steps. So coming to first step, generation of reference DC link voltage. So all of us know, even if you go for active power filter also, DC link voltage maintenance is a prime concern. So DC link voltage plays an important role in the coordinated control of both the converters of UPQC. We have already seen where DC link voltage, DC link connected, its voltage maintenance is the prime concern. Then its voltage always greater than peak value of the grid voltage for the control switching of the converter switches. So DC link voltage should be greater than peak value of grid voltage. And since photovoltaic is directly connected across the DC link capacitor, so it will affect the DC link voltage of the UPQC. So that's why output voltage that is of the photovoltaic should, we have taken a band that is 600 to 800 VDC should lie between 600 to 8. This limit we have taken taking into account the grid rated voltage minimum value we have taken and the maximum value taken taking into account the rated voltage of the DC capacitor. So based on this one, we can select the what should be our range of VDC. Once selected, the reference DC link voltage is decided by P and O algorithm, that is MPPT algorithm. But during non-SPV hour, during non-solar PV hour, the VDC considered as this value we have taken 2√2 VL line to line nominal voltage by √3. So this is regarding how to generate a reference for DC link voltage. Next is for the accurate estimation of power system frequency using variable leaky least mean square algorithm in combination with notch filter. So notch filter is basically a type of band stop filter, very narrow frequency bandwidth, and its transfer function is like this given in equation 1. So where this omega 0 is the notch frequency of the notch filter, and it is to be updated adaptively using this one. R gives the pole radius, because depending on different value of R, the notch will vary. So this is the transfer function of notch filter. Using this concept in conjunction with variable leaky least mean square algorithm, here the estimation of frequency has been done. So here this is the schematic. So whatever equation 1 in Z domain, if you convert into S transfer function, that is similar thing given in the equation 2, that is En. From this En equals to Sn multiplied with this one, then En multiplied with this one. So from this we found out that this is the equation error equation or error expression we have found out from notch filter equation 2. But now the question, this error is to be minimized. And how you minimize? Using variable leaky least mean square algorithm. So these are the steps 3, 4, 5, 6. These are the steps how VLLMS algorithm has been implemented to reduce the error, and to accurate estimate the frequency. So here the 4 steps. That means we have to update the step size, because here step size is involved. We have to update the step size. We have to update the leakage factor gamma, and we have to update the autocorrelation matrix. So after updating all these 3 things, final updation of this frequency is done in using equation 3. So all these equations 2, 3, 4, 5, 6 are implemented here in this figure 2. So this block is for this basically this notch filter. So input given here, the input is the source voltage. So source voltage given as input, whatever equation we have given equation 2, that is implemented here. Whatever error generated, this error fed to for estimation of leakage factor, step size, autocorrelation matrix. After updation of all these 3, final updation of omega occurs here, and this updated omega value fed to this notch filter, so that finally the error will be reduced. So in this way, the accurate estimation of frequency can be done even if there is change in the system, because power system is so dynamic. So even if there is change in load, whatever, then how to estimate the frequency? That estimation of frequency accuracy is required for this unit template generation. Now, so frequency estimation step is over. Next is unit template generation step. But here we have implemented NCF-SO. What is NCF-SO? N stands for normalize, CF stands for comb filter, and SO stands for second order harmonic oscillator. So here, first step is, say whatever our source voltage VABC, using Clark's transformation, we have to convert it into V alpha, V beta. So if you take this V alpha, V beta for our further analysis, then this V alpha, V beta is the uncompensated orthogonal component. Alpha beta means orthogonal component, but this is uncompensated. So if you use this directly for this unit temperature generation, then we may get erroneous results. We will not get the perfect unit template. So that's why V alpha, V beta have to be further processed using normalized CF-SO. So just directly after taking this class transformation, if you take V alpha, V beta, whatever you will get for our analysis, then we will get erroneous error. That's why NCF SOHO is required. Then what is the role of NCF SOHO? First CF SOHO, then normalize. So what is CF? CF is nothing but a COM filter. What it does? Actually, COM filter, say V alpha beta, whatever we obtained using previous slide, converting VS ABC class transformation alpha beta will get. That alpha beta as an input to COM filter will get V alpha beta CF output. What COM filter does? This is the transfer function of COM filter. So the characteristic of COM filter is like this. Whenever there is no change in the signal, the output of V alpha beta COM filter is 0. Whenever there is change, it will show output. That means CF has the characteristic of giving 0 output under steady state condition. In steady state, when there is no change in the signal, then it is steady state condition, no output from V alpha beta CF. So if there is change, sudden change in load, sudden sag, sudden swell, sudden harmonics, at that time, it will show some results. So output obtained from CF, so that means under steady state condition, except during transient or disturbance condition. If there is transient or disturbance, at that time it will show output. Otherwise, in steady state, no output. Then output obtained from CF, that is V alpha beta CF, which is nothing but V alpha CF, V beta CF. We have to take these as input to control and trigger the operation of SOHO, that is second order harmonic oscillator. What is SOHO? So regarding COM filter, already discussed, V alpha beta whatever obtained, we have to feed to COM filter. The output is V alpha beta CF. If there is steady state, then no output. If there is sudden change, then CF has some output. Then what is SOHO structure? Second order harmonic oscillator structure is that is given in equation 9. So its transfer function, if you find out, that is given in equation 10, that is V alpha beta plus divided by V alpha beta CF. V alpha beta plus means positive sequence estimator, V alpha beta plus. So positive sequence estimator and input is COM filter. That is the SOHO. Its transfer function is this one given by equation 10. Now, so we have seen that here the transfer function of COM filter is what? V alpha beta CA by V alpha beta, because output by input, V alpha beta CA by V alpha beta. And transfer function of SOHO is V alpha beta plus by V alpha beta CA. So if you combine both, then V alpha beta CA will get cancelled. So finally we will get V alpha beta plus by V alpha beta, which is nothing but here equation 11. So considering both CF and SOHO combined, multiplying the transfer function of both, you will get equation 11. Now, the objective of deriving 11 is to get the unit magnitude response at fundamental frequency, and it attenuates the non-fundamental component. Hence, magnitude response at 11 at omega 0, we have calculated the magnitude response. Taking S equal to omega 0, we have calculated magnitude response, that is equation 12. But here, in order to find out the gamma at omega equal to omega 0 or omega tends to omega 0, what should be our gamma? In order to know that one, this, if you put omega equal to omega 0 in equation 12, then it will come as an indeterminate term or indeterminate form. So our solution is to use L-Hospital rule. So just like we read in our 12th career, L-Hospital rule to solve this type of equation. So we have used L-Hospital rule twice. And finally, we obtained gamma equal to omega 0 by 2 pi. So now, above consideration of unit magnitude at omega 0, but in the disturbance, if the disturbance in the grid happen, then the magnitude may not get unity. at omega 0. So that's why magnitude at that time will be either greater or less than 1 depending on grid voltage condition. Whether it is sag is there or swell is there, accordingly this omega 0 means magnitude response at omega equal to omega 0 will not be unit T. So that's why what you have to do, then we have to go for normalization. When just like we read in a different means whenever the magnitude goes beyond unity, then we have to go for normalization. Same thing here. So CFSO estimator is modified by introducing a normalization factor. What is a normalization factor? Generally, normalization factor is we have to divide the magnitude mod. So same we have used here. So for implementation and practical implementation, CFSO extractor is discretized, and the discretized domain is given in equation 14. And whatever we have discussed in equation 9, that equation 9 has been derived here, the differential equation, that is equation 16. This equation 16 is implemented here. So just like we have discussed, V alpha beta whatever obtained fed to COM filter, the COM filter output fed to second order harmonic oscillator. So this V alpha beta fed to this C equation 16, this is implemented here. This one implemented here. And whatever V alpha beta 1 plus obtained, so then it goes through this matrix. This matrix is nothing but this one. So whatever we have discussed, so now up to this means figure 4 normalization we have not implemented. We have implemented this next slide. So anyway, V alpha beta plus whatever positive sequence extractor will obtain, from that we'll find out our unit template. This is our objective, is to find out unit template. This is just the figure without normalization. But for improvement, we have used normalization. Just like we have used normalize means we have to divide the magnitude. V alpha beta, V alpha 1 plus square, beta 1 plus square, root over we have divided. So this thing implemented here, normalization. So after normalization, whatever we have discussed previous slide, this V alpha beta plus we obtained, and from V alpha beta using this domain alpha beta to ABC, we obtain unit template. And here, this is the rotation matrix. What is its role? Because while in the discretization process, some delay has been included. So to compensate this delay, rotational matrix we have implemented. So now V alpha beta plus we obtain, from V alpha beta plus unit templates are generated. So basically what we have discussed, frequency we have found out using VLLMS notch filter, taking that frequency using NCF Soho, we have determined our unit template. Now question, how from unit template we will generate our reference signal, and finally reference signal is used for switching signal generation. That we will see now. So here, just like whatever discussed briefly given, VS ABC domain to alpha beta domain. Then using this notch filter, we have found out this omega 0, and this omega 0 has been used for NCF. So, and finally, these are the three things we have whatever discussed till now, that is UIA, IB, IC, unit template we have generated. Taking this unit template means only template, no value. So value we have to, how much is the value, magnitude you have to multiply. So that magnitude is V line to line nominal into 2 by root 3, this thing implemented. This multiplied with UIA gives us VLA reference. Same thing multiplied UIB, LB reference. Same thing multiplied UIC, VLC reference. So these things are implemented here up to this VLA, LB, LC reference. These are to be compared with the source voltage SA. These are to be compared with the source voltage SASBSC and this injector signal generated. This injector signal is to be compared with the accurate injected signal. So then error fed to hysteresis current controller for switching signal generation to series compensator. So these things are shown in the equation 19, that is how to generate VSC, a reference, injected signal reference, LA reference minus VSA, LV reference minus VSB, like this. So 19 is here implemented. This compared with the actual error fed to hysteresis signal for switching signal generation. So this is one part. How the switching signal for voltage related power quality issues, how to generate switching signal for this series compensator. Next is for parallel or shunt compensator. So for parallel or shunt compensator, what are the steps? Arnav sir, some disturbance is there. Hello.
All subject to my academic subject, my own subject, and my own subject. खालचे 3 subject मध्ये करायचं.
Hello.
खालचे 3 subject कोणत्या इथं माहिती नाही. आणि आपण का कुछ घेऊन बघायचं. हां? कोणाला?
Arnav sir, are you there?
आता जेवण करायचं, आपल्याला हॉस्पिटल जायचंय.
Pranati, are you there? Pranati.
कुठे?
Hello. Pranati, are you there?
Sir, better you call them on phone, sir. I guess they have not.
Okay, okay. Okay. So reference signal generation approach for the parallel converter. Whatever you have discussed, that is for series converter over. Next thing is for parallel converter. So parallel converter, what are the different steps? Parallel converter mainly 3 steps. That is fundamental active current component of load current by using notch filter. How to estimate or find out fundamental active current component of load current. Then what is the switching loss compensating component by regulation of DC link voltage? That means if you will regulate DC link voltage, then some current is required. Then that current we have to draw from the source. That is nothing but the switching loss component. And what is its value? How to estimate or how to calculate, that also we'll discuss. And another is contribution of PV towards load and grid. That means since here PV support is there, so how much is the equivalent current PV is providing AC equivalent current, that also we have to find out. So from these 3 components we will find out our reference signal generation. So first step is regarding fundamental active current component of load current estimation by using notch filter. So here this is nothing but the notch filter that already we have discussed in the during series compensator case analysis. So here what happens when input load current given to this notch filter, then whatever Ez it will come, that Ez will contain all other components except fundamental. So if these all other component will able to subtract from its original component, then obviously we'll get our fundamental component. So this is the simple thing we have implemented. That is, the connection is just an inverse notch filter type of thing. So that means whatever notch filter output will get, that output is to be subtracted from the original signal. Then finally we'll get this, whatever signal will get, that contains fundamental. So this whole implementation is like this. So here the resultant notch filter obtained behaves as an inverse notch filter, allowing fundamental frequency signal and attenuating signal with the rest of the frequency. All other harmonic content or rest of this frequency signal are attenuated. So this is the implementation in figure 6. Now, whatever fundamental component we obtain, that still may contain the reactive component. So we want fundamental active component, that is our motto. So whatever we obtain using figure 6 schematic, that may contain some reactive component. So now our job is to segregate that reactive component so that we will get only active component of fundamental current. So for that, reactive component, how to segregate or separate? By using quadrature unit template scheme. So what is that? That expression is UQA, QB, QC. How to find out this thing? This thing will find out from the in-phase unit template, because in-phase unit template already discussed. UIA, IB, IC, how you have generated already discussed. So those IA, IB, UIA, IB, IC, taking these three, we can find out UQA, QB, QC. These are nothing but called quadrature component. So now the quadrature template. Now quadrature template is to be fed the zero crossing detector. What it will do? To determine the instant when the quadrature component magnitude goes to 0. So that means our objective is to remove this reactive component. For that, whatever UQA, QB, QC will find out from this equation 23, that will fit to zero crossing detector. So zero crossing detector, what it will do? It will find out, or it will determine the instant at which when the quadrature component magnitude goes to 0. At that instant it will hold, that is using sample hold circuit. So that instant will pass through this IFL, ABC, whatever you obtained in figure 6, that we have to pass through. Then we have to take absolute value of all these three cases, then take average. Finally, whatever you will get, that contains the only fundamental active component, because we have blocked this reactive component current using ZCD and sample and hold circuit. So these things are implemented in equation 24. So IF average become IFPA, PB, PC by 3. So whatever you QA, QB, QC obtained, that passes through ZCD, zero crossing detector, at that instant will feed, will sample and hold, and at that instant will feed IFL ABC, then taking average absolute value and then average will get IF average. That is our first part. Out of the three part, first part is this one. Next part is just like the switching loss current component and PV feed forward component. So what is switching loss component? Because to maintain DC link voltage, some component of current is required. So what then? That much current we have to draw from the source. Otherwise, there will be imbalance. Who will provide that current? For maintaining DC link voltage, some current component is required. And who will provide that? So for that, you have to draw from the source. So how much we will draw? That is nothing but the IDC component. So this is given in equation 26. That is error voltage is VDC reference minus VDC. This error passes through PI controller and we will get this DC component. So the IDC is nothing but switching loss current component. So now we obtained two things. One is switching loss component, another is IF average. And next is the PV feed forward component. What is that one? This PV feed forward component is nothing but how much PV is providing that DC current, its equivalent AC is the PV feed forward component. So that we will find out IFPV equal to this expression. This expression is derived not just from the power expression, 3V phase I phase cos phi, like this power expression. After some mathematics, this expression is derived. So now we obtained three things. One is IF average, previous slide, and this slide IDC and IFPV. So these things, whatever we have discussed in equation, these are implemented here. VDC reference, VDC passes through PI controller, IDC obtained. Just whatever we have discussed, equation 26. Similarly, V regarding IFPV, ILLVLC using this expression, this expression is to divided with product is this one VPV IPV. So that this is the implementation of equation 27. So in this way we obtain IFPV. So three things we obtain now. First is IF average, second is IDC, third is IFPV. So now from this we will find out our reference. So now IS reference is sum of IF average IDC minus of IFPV. Why minus? Why these two are plus, this is minus? Because these two takes current and this one feed current, feed forward, feed. Since it is feeding, we have taken negative. Those who are drawing, we have taken positive. So this is nothing but IS reference. This IS reference is nothing but the magnitude. So in order to get a signal, you have to multiply with unit template. And unit template, how you have generated, that already we have discussed. So this IS reference multiplied with unit template A in phase, UIA, in phase unit template A, multiplied with unit template in phase B, unit template in phase C, will get ISA reference, ISB reference, ISC reference. So these are implemented here. So whatever you have discussed, so here now ISA reference, ISB reference, ISC reference. These references are compared with the actual ISA, SB, SC. Whatever error signal generated, fed to the hysteresis current controller to generate the switching pulses for switching of the parallel converter. So this is the total overall schematic. Just I am discussing in brief. VS, ABC, whatever ABC domain to alpha beta, NCF SOHO, and using adaptive notch filter omega find out, and these NCF SOHO found out U, QA, QB, QC, and from this omega 0 fed to notch filter and ILABC. So using this we will find out IFL ABC. Detail we have discussed already. IFL ABC how found out. Then IFL ABC using IQA, QB, QC, ZCDSH, absolute value 1/3, that is average, will get IF average. IF average in this way, IDC, IFPV already discussed in previous slide. So these three come together, these two are added and this one minus. So in this way you will get IS reference. This IS reference multiplied with UIA, IB, IC to get ISA, SB, SC, compared with actual value, error signal fed to hysteresis current controller for switching signal generation of parallel converter. So in this way, the control algorithm how implemented for switching signal of both the converters we have discussed. Now coming to the simulation. So these are the different grid voltage, different values, different parameter values taken during simulation. Now coming to the results. So here first result is under grid voltage sag and nonlinear load. So that means load is nonlinear and so the voltage sag is there, means voltage is not perfect, means sag is there. From the normal value, some value less than the normal sag. See here, up to 0.2 second, voltage is normal, 0.2 to 0.3 sag created. So this is which voltage? This is not ABC. From ABC to alpha beta, that alpha beta voltage is this one, orthogonal component. So this V alpha beta, as per our analysis, this V alpha beta we have fed to what? Regarding series compensator, we have fed to COM filter. The output of COM filter is what? When there is steady state, see up to 0.2, the no output of V alpha beta COM filter. And at 0.2, some changes is there. What is that change? Sag is there. That's why it shows output. And after some time, the sag continues, so no output. So this is V alpha beta COM filter output. Then using this V alpha beta COM filter, it fed to NCF SOHO. And this is the output of NCF SOHO, V alpha beta 1 plus, positive sequence extractor. In positive sequence extractor, we came to know that still sag is visible in V alpha beta 1 plus. So for that, what is our solution? Our solution is we have to go for normalization. So after normalization, V alpha beta plus. So now it is normalized between -1 to plus. Using this normalized V alpha beta plus, unit templates are generated. Then these unit templates are used for switching signal generation of the series converter. So these are the what is the injected signal. So these are the injected signal in the series compensator. So now see VS ABC, here the voltage dip or sag is there over 0.2 to 0.25, but now after injecting this signal it is compensated. So this is the final VL ABC using the controller of series converter. This is regarding the voltage sag case. Then also the signal is non-linear. So that means harmonics present. So harmonics present means who will act for that? This shunt compensator or parallel converter. So this is highly distorted current. So this is the shunt compensator injected current, then highly compensated and highly distorted, and this much injected. Then now this becomes sinusoidal. So this is parallel converter performance during sag. And also you can see that the DC-link voltage is maintained with little bit latching is there, but this DC-link voltage is able to maintain even if sag is there, even if distortion is there, able to maintain DC-link voltage. This is regarding the TSD of load current, initially in 26.16, now after implementation 3.34% reduced. Next thing is, just like we have discussed, now so many entities are there, grid is there, load is there, both the converters are there, PV is there. So how to manage power or how to distribute power, that is active power distribution as well as reactive power distribution. So these are the figures that see for series converter up to 0.2, there is no problem because signal that is at the nominal voltage. So from 0.2 onwards, there is sag, that's why it injects signal. So, and how much? So that PSC amount of active power is consumed by parallel converter. That's why parallel converter is like this, consumed by parallel to make it available for series converter during sag. And this is the red one is the load active power. So this is regarding how active power distribution occur, who will share how much to meet a particular load demand. And this is regarding the reactive power distribution, where the load reactive power is balanced by parallel converter reactive power and grid power equal to 0. So grid power equal to 0 here merges in the 0 line, and series converter reactive power is also 0, merges here. So that means you can claim that in phase compensation of sag is carried out, no effect on the reactive power curve. So this is regarding the swell case. So just like previous case we have discussed, sag case, voltage deep down, deep, but here the voltage swell. Also nonlinearity is there, nonlinear load. See, same way from 0 to 0.2, it is at some level, from 0.2 to 0.3, voltage level increases. So V alpha beta output like this, COM filter output only shows during disturbance. Then positive sequence extractor output, it shows output, but only thing is the swelling is also visible. To
Sir,
make
one point, sir.
Yes.
Sag has occurred at 0.2 and you are creating swell also at 0.2.
0.2, right.
Right,
This is
okay.
another signal, another signal.
Acha, okay. Right, thank you.
Another
Sorry
instant.
for
Yeah, no issue. So V alpha beta plus after normalization, this is the value. So taking this V alpha beta plus after normalization, we have found out that unit template, and from unit template, we have found out our reference signal, then reference signal, actual signal compared, switching signal provided for switching of the converter, and from the switching, the injection occur. So VSC, this is the injected signal. So here 0.2 to 0.25 swelling is there. So now this much is the injection. Because of this one, now our VLABC at level, so that swelling is compensated. Same thing for nonlinear load case also, because here nonlinear load is there. That means whatever discussed say case nonlinearity, here also nonlinearity. These are the injected signal. Now this is the sinusoidal signal we are obtained. And here also DC link voltage is perfectly maintained. TSD also reduced. Now coming to power distribution, active power distribution and reactive power distribution, just like we have discussed in sag case, swell case is also there, but swell case, the PAC amount of active power is consumed, and previous case a provided power voltage, now voltage consumed. That's why the pink color is like this, dips. Consumed means dips below zero. So consumed by the series converter and fed to DC link, as series converter is injecting negative voltage to compensate swell. Swelling is there, we have to inject negative voltage, then only you will get the perfect voltage. So these are the different distribution between the PV, grid, load. And so far as reactive power distribution is concerned, this is same way as to that of sag case. Q load and Q parallel converter, they are both balancing. Grid reactive power is 0 and series converter reactive power is also 0. This is the case when the system is having harmonics in both grid and load. That means load current is disturbed, having harmonic. Grid current is also disturbed, having harmonic. Grid voltage is also disturbed, having harmonic. Previous case we have seen grid voltage having sag and swell, sag or swell, but now having harmonics. So see, up to 0.2 that is okay, 0.2 to 0.3 harmonics is there. That's why COM filter output is shown from 0.2. After some time again same continues, so no changes, so that's why 0. So V alpha beta 1 plus, just like previous case seen. So to normalize V alpha beta plus, this one, using this one unit template generated, then the reference generated, then injection signal. So VSCC is the injection signal, this one. So now this is the voltage with so much of harmonics, and now this is the compensated voltage by eliminating harmonics. So this is the TSD content, and now TSD content reduced after implementing this algorithm. Same way for this load also highly disturbed or having highly harmonic component. These are the injected signal. So now it is sinusoidal after injecting this signal. And this is regarding the maintenance of DC link voltage, almost smoothly maintained. If you in the zoom figure, maybe disturbances very small, that is 1 or 2 volt maximum. And this is regarding active power distribution and reactive power distribution for the case with harmonics. So this is the figure or the photo. This thing, whatever we have discussed, this thing implemented in the laboratory developed prototype in the hardware environment. So here, this is the micro lab box, or you can use DSpace for this implementing the control algorithm. So your control algorithm is to be dumped to the DSpace or micro lab box. So the UPQC having 2 converter is here. So 3-phase rectifier load sensor boards for sensing the different current and voltage signal and fed to the controller, that is micro lab box. First sensing, then fed to the controller. Then from the controller, output goes to the converter for switching signal generation. And all these waveforms are taken through this DSO. And these are the different coupling inductor, this RC filter, just like the things we have seen in the schematic. So many things are there. RC filters, coupling inductor, and this is the series injection transformer. Just like in the schematic, we have seen that injection transformer is required for injecting voltage. So this is the series injection transformer. So that means whatever schematic we have discussed, that is implemented in laboratory developed prototype like this. And these are the different parameters taken. Now coming to hardware result. So performance under nonlinear load condition, when load is nonlinear, so say, but there is no disturbance in the source voltages, say VSA, VSB, VSC, 3 voltage, because we are having a 4-channel DSO only, not able to show all the 6, means VSA, SBC, VLA, LV, LCC, LC at a time, because we are having 4-channel DSO. So that's why here VSA, SBSC, and VLA here, VLB, LC here. But here, since the source is not disturbed in this case, so that's why the injected signals are not appreciable or visible. So these are close to zero injected signal. But in this case, what happened? Load is nonlinear. So nonlinear load means compensating signal is to be properly visible. So these are the compensating signal. Parallel converter signal, IPAC, parallel converter A, parallel converter B, these two, and here parallel converter C. So when load is nonlinear, these are the injecting signal, so that we will get our grid current now become sinusoidal. So this is the grid current become sinusoidal. And what about THD in each case? THD for before compensation is of the order of say 24, 25 like this, 25, 25, 26 different phases, and after compensation is the order of 3, 4 up to 3, 2 point something, 3 point something like this in different phases. So THD is very much reduced using this algorithm. Now coming to SEG case, just like SEG we have discussed in simulation, here also SEG we have found out results using our hardware. So SEG means this here, the SEG occurs, means voltage level dips around 25%. So VSA, VLA, VSB, VLB, like this we are shown. See in the zoomed view, so SEG signal are there, means signal less than the normal. So just like in 3 phases, SEG is created. So when SEG is there, to compensate SEG, we have to inject signal. These are the injection. One is this one injection, another is another phase this one, and for the next phase in this line, in this scope. This one is VSCC, and VDC link, DC link voltage also maintain constant. This is about voltage during SEG case, and also current is nonlinear. See, current is nonlinear is I parallel converter current A, B, C. These are the high nonlinear current also, because this case voltage is same, current is nonlinear. So these are the current nonlinearity in the current, different phases A, B, C. So nonlinearity is current. These are the injected signal. To compensate the nonlinearity, we have to inject signal using parallel converter. These are the injected signal in ABC. Now the compensated current become sinusoidal. So just like that we have discussed, next is the swell case. Here swelling is around 40% taken. So this is the from the figure we can see that from this level swelling occurs. So in the zoomed view also we can see that signal is one level, swelling another level for all the 3 phases A, B, C. And these are the injected signal to compensate swelling. This is injected signal for A phase, for B phase, and the next scopes for C phase. So these are the injected signal to compensate swelling. And another thing is also load is nonlinear load current is there. So these are the A, B, C nonlinearity in load current. So and VDC voltage is maintained. Then since nonlinearity is there, zoomed view, so to compensate nonlinearity, we've injected signal. So now this is our after compensation signal, VSA, SBSC, no nonlinearity. This is no nonlinearity. This is the load current. These are the injected current. So after giving the injected current to this nonlinear current, we get this sinusoidal current. So the conclusion is that in both simulation as well as in laboratory developed prototype, we have seen that the combination of adaptive notch filter and NCF, so whatever we have discussed, so it is efficient enough to adaptively generate switching signal, means whenever there is disturbance in the load, that it has taken into account and accordingly it generate switching signal. Let it generate switching signal now. After this instant, some changes occur in the power system dynamics. It also adapt that one and accordingly it will generate switching signal using unit template under different non-ideal condition of grid and load, and able to successively mitigate the cases of voltage unbalancing, that is sag, swell, harmonics, and compensated reactive power also, because we have already seen the result, reactive power is 0. So that the unit power factor operation at PCC occur. Then also you have seen how to meet a particular load demand. The power has been shared by grid, load, PV. That is power management done properly. Then DC link voltage also smoothly regulated. So from this we can claim that this analysis can be used for improving both voltage and current quality. That is EPQC can improve, this EPQC arrangement can improve both voltage and current quality using the suggested algorithms. Thank you. Thank you all. Any question?
Really super, sir. You made it. You showed the legacy as a the head of the department. Very good. It was excellent, sir. Nice.
Thank you. Thank you so much.
I guess if there are no questions from any other, I want to ask, sir, this ANF, as you said in the conclusion, ANF and NCF SOHO,
Yes.
can we use for other applications also, sir? Like normally
Yes.
we generally use
Actually,
3-phase to 2-phase, and you do no?
Yeah, actually, these are the algorithms. Basically, they have started, means people started working on this algorithm in the signal processing, this communication signal processing area. So now what power system people do, basically different signal processing techniques they have applied to power system. So we can use for power system harmonics estimation also, power quality improvement also, this thing can be used. Just like the VLLMS algorithm I have shown here, this algorithm I have already implemented for frequency estimation only and for harmonics estimation also. And here this VLLMS algorithm I have combined with the notch filter for this type of application. So just you can get idea, because new idea you can get from this signal processing area. So that idea, that technique, because basically signal is same, means signal processing, signal they are processing. Here also this signal means power system signal, disturbed signal we are also processing to get some results. So it can be applied to different areas also. Also forecasting also we have applied different algorithm, just like that ensemble Kalman filter, that is one of the area technique from the system identification technique. So if we apply some different techniques, maybe they are originated maybe in the signal processing area. If you apply to power system area, that may be to some extent new. Or you can say, or you can claim something that something new is there, so far as application is concerned.
So thank you, sir. Thank you.
Thank you.
Sir, another one, you said in the beginning that solar image capture, now forecasting and all. I mean, in
Yes.
India, we have not started, but abroad they have started, like
Yes.
they're using. Like,
Yes.
can you I mean, throw some light on that one, sir? Like, it's very interesting. Like,
Yes. Actually, this work I have done during my postdoc at NTU Singapore. This solar irradiance forecasting using sky image. Actually, what happened that in Singapore, that NTU Electrical Science building is just like a H-shaped, English letter H. So in the means H having two sides, in between one connection is there. So in the two side H, so they have installed sky imager in the building. That is a 7th floor building. So I have gone to that 7th floor building, and there are also technical assistant they have installed. I have seen there. So actually they have installed some image sky imager. That sky imager, it will point to the sky, and it will capture sky images each 30-second duration, one image, and it will send to server. And the server taking that images, we have to analyze. And how to analyze? Just like I have discussed, take 1 minute, one now image, 1 minute ago image, then 1 minute, maybe 4 minute, 5 minute ago image. Then you can compare. If 1 minute ago image, for example, total cloud we have divided into 3 types. One is thick cloud, another thin cloud, another clear sky. For example, a sky image having 3 things mainly. We may divide more also, but for analysis, let us take 3. Thick cloud, thin cloud, and clear sky. So we'll analyze if this is the image now, and after 5 minutes, which portion of the image will cover the sun. For example, we'll analyze that. I have some presentation that one, but today I'm not showing that one. So after 5 minutes, after 15 minutes, which portion of the cloud will cover the sun? That will analyze using image processing technique as well as some optical flow algorithm. Say we'll find out that thin cloud will cover the sun. If thin cloud will cover the sun, then how much is the irradiance? That irradiance should be more than the thick cloud will cover the sun. And how much that one, that some calculation is there, analysis, everything is there. So then based on that, and it also depends on which area you are finding out, latitude, longitude, all these things you have to take into account. For example, at Rourkela, on today date at Rourkela means day number also you have to take into account. Means for example, today is November, say 8th November having some day number. Just like January 1 is day number 1, December 31st is day number 365. Similarly, November 8 will get some day number, maybe 300 something. So on that day number, at Rourkela, having latitude this one, if thin cloud will cover this sun, then how much irradiance we will get? Using that analysis, we can find out. And in that analysis also, we can use different AI ML techniques or whatever, also different soft computing techniques, AI ML technique for getting the more accuracy. So these study means already carried out at Singapore, also different European countries they are doing, but in India it is very early stage now. Thank you.
Thank you, sir. Thank you.
Okay, then Arnav sir, are you present?
Sir has gone for some work, sir.
Okay, Pranav.
If any questions from the participants, otherwise we will conclude.
Sir, thank you, sir, for your good session, sir. I am quite out, sir.
Okay.
Okay.
You are busy having
Thank you very much.
so many activity at a time you are doing.
Madam also, Archana madam also calling me. Okay, sir.
Yeah.
Okay. Thank you.
Okay. Okay, if no more question, then I'm leaving. Thank you all.
Thank you, sir. Thank you very much for sharing your knowledge with us.
Sir, thank you once again. Thank you.
Thank you.
This is for the information of the participants that the next session will start at 3 p.m.